We have spent most of our work thus far in the class studying and finding solutions to differential equations. But will we always be able to find such a solution? In other words, what if we're looking for a solution that doesn't exist? And what if we find a solution, but there are other solutions that we're missing? For a non-differential equation example, the equation x squared equals 1 has two solutions, 1 and -1. Just because we find one solution doesn't mean we found all of them. To answer this, we have a theorem called the existence and uniqueness theorem for first-order linear equations. It says that if functions p of t and g of t are continuous on the open interval t between alpha and beta that contains the initial point t equals t naught, then there exists a unique function y equals y1 of t that satisfies the linear differential equation y prime plus p of ty is equal to g of t for all values of t on an interval from alpha to beta, where this solution also satisfies the initial condition y of t naught equals y naught. While we won't prove this, the proof of this relies on the existence of the integrating factor mu equals e to the integral of p of t dt. But even without proof, we can use this theorem to answer our questions above. The existence of a solution tells us that there is a solution to be found. In other words, we're not on a wild goose chase looking for a solution that doesn't exist. And the uniqueness of a solution tells us that if we do find a solution to an initial value problem, at least with linear equations, it's the only solution. Combined, this tells us that every initial value problem with a linear differential equation has a solution, and if we find the solution, it's the only one. But this theorem is only for linear differential equations, and we've already seen some examples, such as separable differential equations, that are nonlinear. So what about differential equations that are not linear? For this, we have another theorem. The existence and uniqueness theorem for first-order differential equations says that for a differential equation y prime equals f of t and y, where f of ty and the partial of f with respect to y are continuous on some rectangle for t values between alpha and beta and y values between gamma and delta, containing our initial point t naught y naught, then some subinterval t between t naught minus h to t naught plus h, contained in that continuous interval t between alpha and beta, then there is a unique solution y equals y1 of t to the initial value problem y prime of t equals f of ty, with y of t naught equal to y naught. In the proof of this theorem, we don't have the tools to do in this course, but is proved in future courses. An important graphical note that I would like to make about this theorem is that the uniqueness of solutions guarantees that the graphs of two solutions of differential equations cannot intersect. If two solutions were to intersect at a point AB, then those two solutions would both solve the initial value problem with the given differential equation and initial condition y of a equals b, contradicting the uniqueness. So when we draw our integral curves, or solution curves, we need to make sure that they never intersect. Now let's look at an example where we use this theorem. I want to find the solution to the differential equation y prime equals y squared, where y of 0 is 1, and find the interval where the solution exists. Since this is a nonlinear differential equation, y prime equals y squared, we'll need to look at our uniqueness and existence theorem for nonlinear first-order differential equations. And we need to check that f of ty and the partial of f with respect to y are both continuous. Since f of ty equals y squared and the partial of f with respect to y equals 2y are both polynomials, they are continuous for all real numbers. So we know that a unique solution exists on some interval for t between a and b on the real number line. And since the differential equation is separable, we have tools to be able to solve it. We'll divide by y squared on both sides, and integrate y to the negative 2 times y prime equal to 1. On the left, we'll get negative y to the negative 1, while on the right, we'll have t plus c. Multiplying by negative 1 on both sides and taking the inverse, we get that y equals negative 1 over t plus c. Note here that the constant c changed from one line to the next, but it's still just some constant. And now that we found this solution, up to the constant c, we can impose the initial condition y of 0 equals 1 to find what c is. Plugging in 1 for y and 0 for t, we get that 1 equals negative 1 over 0 plus c, and thus c must be negative 1, giving us the solution y equals negative 1 over t minus 1, which is equal to 1 over 1 minus t. But using the theorem, we can say a bit more. We know that this solution exists and is unique on an interval for the real number line. But notice that this solution has a discontinuity at t equals 1. So the largest interval on which the solution that includes the initial data point t equals 0 is the interval from negative infinity to 1. The interval from 1 to infinity doesn't include our initial data point 0. So the existence and uniqueness theorem guarantees that the differential equation y prime equal to y squared with initial condition y of 0 equals 1 has a unique solution y equals 1 over 1 minus t on the interval from negative infinity to 1. We refer to this interval where the solution exists and is unique as the interval of existence of the solution. And we cannot guarantee that after this discontinuity, this function is still the solution or that it's unique. So our theorems for linear and nonlinear differential equations tell us that unique solutions to these differential equations exist. But they do not guarantee that we can find them. Such as the last example where we needed to use our methods of solving separable differential equations. But sometimes we may not have a method to find a solution. Or even worse, sometimes we cannot find solutions because the solutions cannot be written in closed form. In other words, the solutions can't be written in terms of our usual functions like sine, cosine, polynomials, logarithms, etc. So what do we do if we know that some solution function exists but we can't find it? For this, we'll need some numerical methods to find approximations to solutions. And in practice, in applications, these approximations are as useful as the actual solutions. One such numerical method that we'll study is called Euler's method, which we'll cover soon.